Alright, this video is going to go through some of the in-text questions for chapter 18. Having a look at them, there's quite a lot, so we'll break it into two videos, I think. Alright, question 1. So, question 1 says, use table 18.1, so it's a bit above, to see if you obtain the correct refractive index of the material by dividing the velocity of light in air by the velocity of light in the material. So if we scroll up, we have a bunch of mediums here. They're listed down the side. You've got their velocity of light. Now, they've only given you the actual absolute number, so 3.00, 2.31, 1.90, etc. Because if you check in the heading there, you can see that there's a 10 to the 8 listed. So all these numbers should be multiplied by 10 to the 8 to get the actual velocity. And then we have the absolute refractive index of the material. So remember, the absolute refractive index is relative to air or relative to the vacuum. So we want to know, well, do we get n to be the same? And n, remember, equals c over v. And what is c? C equals 3 times 10 to the 8 meters per second. That's the speed of light in a vacuum. Now, air is a little bit under this, but we're just rounding off to 3 in this case. I'm going to do a couple of tests. Let's do air first. V equals 3.00 times 10 to the 8. N equals c over v equals 3 times 10 to the 8 divided by 3 times 10 to the 8. Well, that's going to be the same, equals 1. And if we have a look at the table there, we see that the refractive index for air is 1. Okay, let's pick a couple of others. Let's do water. So for water, V equals 2.26. And so let's do that. N equals c over v equals 3 times 10 to the 8 over 2.26 times 10 to the 8 equals, and let's put that in. Now, but do be careful with this, because with this times 10 to the 8, if you're not careful with brackets, or you haven't used your times 10 function, times 10 to the power function correctly, commonly what will happen is you'll do 3 times 10 to the 8 divided by 2.26, which will give you a number. In this case, it'll give you some multiple of 1.33, and then multiply by 10 to the 8 again, and you'll end up with 1.33 times 10 to the 16. Okay, so you've got to make sure, so sometimes it's best to do that number divided by and put that whole number in brackets, just to make sure that your calculator is doing what you want. Okay, that's why I keep saying you've got to practice with the calculator. So let's put that in. 3 times 10 to the 8 divided by 2.26 times 10 to the 8, and we do get 1.33. It's giving us 1.327, so slight rounding error, because don't forget we're using a rounded air, we're not using the absolute value of air. The real value is something like 2.999956 or something. Okay, now there's a way to make this a little bit quicker on our calculator. Let's do zircon. V equals 1.58 times 10 to the 8, N equals c over v equals 3 times 10 to the 8 over 1.58 times 10 to the 8. Now, as I said, these times 10 to the powers can be tricky if your calculator usage is a little bit sloppy. If, though, we think about this, what we're seeing here is we've got this times 10 to the 8 on top, this times 10 to the 8 on the bottom. These times 10 to the 8s, these times 10 to the 8s cancel. And we're left with 3 over 1.58, which is a lot easier to get right in your calculator. And we end up with 1.90 or 1.8987, but let's round it to the same decimals they're using. You can do the rest on your own time. Okay, question 2. Calculate the index of refraction for light going from air to a material in which the speed is that, so we've got a couple of theirs, and there's a secondary prompt there, is answer C possible? Explain. So, again, we're after index of refraction. We just saw that the formula for that, N equals C over V. C equals 3 times 10 to the 8 meters per second. So, let's chuck it in. N equals 3 times 10 to the 8, and we see that the first one, we've got a value of 2.6 times 10 to the 8 to use. Okay, we're given that as a velocity. That's going to be the same as 3 over 2.6. And we get 1.15. Remember, no units for refractive index. B, we're told velocity is 1.8 times 10 to the 8. So let's write the equation. N equals C over V equals 3 times 10 to the 8 over 1.8 times 10 to the 8 equals 3 over 1.8 equals 1.67. Now finally, again, this number should stand out as being a bit of a concern. 3.4 times 10 to the 8. Think about why. Let's work through it for the moment. 3.4 times 10 to the 8. So let's follow the exact same procedure. 3 times 10 to the 8 over 3.4 times 10 to the 8 equals 3 over 3.4. This should start popping up a concern. We're doing a division by a bigger number. That means we're going to have less than 1 as our answer. And we find that it is equal to 0.88. Now, this is two problems. One, this is the cosmic speed limit, 3 times 10 to the 8. But this number is bigger. How can it be bigger? If nothing can go faster at this, then what's this? So there's problem number 1. 2, this is less than 1. Okay? Absolute refractive index relative to a vacuum or relative to air can never be less than 1. Alright? Relative refractive index, when we talk about what is a refractive index between two different mediums like glass and water, that can be less than 1 depending on what direction you go in. Okay? But an absolute refractive index, that cannot be less than 1. That's saying it's actually speeding up light. And we can't speed up light by shining it through something. When we shine light through something, it always slows down. Perhaps in the future we will find something that does do that, or we'll create something. But for now, light can't go faster than this speed limit. So this number, too big. This number, below 1. Those are the problems, which is why it's impossible. Okay, this time we want to find the speed of light in a medium whose refractive index is a couple of different numbers there. So we want to find out what is V. We know that C is 3 times 10 to the 8, speed of light, and we're given n values there. So for A, n equals 1.5. So n equals C over V. Let's rearrange that to get V on the side. We find therefore that V equals C over n. Let's substitute. Now this one we have to put the whole thing in. 3 times 10 to the 8 divided by 1.5, and we're going to get 2 times 10 to the 8 meters per second. Don't forget your units. B, n equals 2.4. So V equals C over n equals 3 times 10 to the 8 over 2.4 equals, so 3 times 10 to the 8 divided by 2.4 gives me 1.25 times 10 to the 8 meters per second. And finally C, n equals 1.3, V equals C over n equals 3 times 10 to the 8 divided by 1.3 equals 2.31 times 10 to the 8 meters per second. And that did 2.3, but 2.31's fine. Okay, so there's question 3. Let's head down to question 4. Okay, so question 4, we are starting to look at some Snell's law stuff. So we're told use figure 18.3, that's to the left there, to calculate the refractive index of the material. So it looks like this. Okay, so that's our 90-degree angle. We've got an angle of 65 degrees, 30 degrees. We know this is air, and we know this is some material, which means that n equals 1, n equals dunno. let's list off what we have. N1 equals 1, theta 1 equals 65, theta 2 equals 30, okay, and N2 equals, don't know. Remember though that in this case our angle is between the principal axis and the incident line, so the perpendicular line here, which we have. If it was down here, we would have to figure out what is the complement and use this angle. This is Snell's law. N1 sine theta 1 equals N2 sine theta 2. Let's substitute. 1 times sine of 65 equals N2 sine of 30. So the 1 cancels. We can rearrange that, take that sine over. So N2 equals sine of 65 over sine of 30. Okay, let's do that. Sine 65 divided by sine of 30 gives me 1.81. Okay, let's do our next bit. 5. Okay, we've got a table. Tables are really common with these sort of basic applications of laws where you're just practicing doing substitution for different bits. So we've got angle of incidence, angle of refraction, and refractive index. So we can think of this as we've got theta 1, theta 2, and we've got n of 2, because if we read the question, it says complete table 18.2 for light rays passing from air. So our original n is 1 to a different medium, and they've listed it there. So we see for option A, we've got to figure out what n is. For option B, we've got to figure out what r is, or the second angle is, or refracted angle. For option D, we've got to figure out the incident angle. For option D, though, we're missing 2. Okay, one of these we can solve, the other we will not be able to solve. So let's wade into this. So for A, we know that n1 equals 1. We know that theta 1 equals 30. We know that theta 2 equals 20. Well, this is just the same as what we had here, isn't it? What we don't know is what our second n is. Okay, let's use that same equation that we had there before. N2 will equal sine theta 1 over sine theta 2. Okay, and that would be multiplied by n1. Now let's substitute. Equals sine theta 1 is 30, sine theta 2 was 20, n1 is 1, so it doesn't matter. And this is just a number, so let's calculate that. Sine 30 divided by sine 20 gives me 1.46 for n. And double check our answer. 5. Yep, great. Okay, let's do B. We have now n1 equals 1. We have theta 1, our incident angle equals 60. We don't know our refracted angle, but we do know that n2 equals 1.8. Substitute n1 sine theta 1, n2 sine theta 2. 1 times the sine of 60 equals 1.8 times the sine of our unknown angle. Let's rearrange. Sine of theta 2 equals sine 60 over 1.8. And so theta 2 equals the arc sine of sine 60 over 1.8. Sine 60 divided by 1.8. Take the arc sine. We get that theta 2 equals 28.7 or 8 degrees. 8 degrees. They have 28.7. I like to put the whole thing into the calculator. It does require a bit of extra precision, and so that's within rounding errors. Don't stress about stuff like that. See, this time we have n1 equals 1, still here. Theta 1 equals, I don't know. Theta 2 equals 40. N2 equals 1.4. Snell's law. n1 sine theta 1 equals n2 sine theta 2. 1 sine theta 1 equals 1.4 sine 40. The one we can ignore. Let's rearrange. We can take the arc sine theta 1 arc sine of 1.4 sine 40 equals, so sine 40 multiply by 1.4, take the arc sine, and we get that it equals 64.1 degrees. Alright, now let's have a look at D. So we don't have two bits of information. We've got one bit of information. We've still got that n1 equals 1, but let's see what we get. D. n1 equals 1, theta 1 equals 0, theta 2 equals dunno, n2 equals dunno. Let's write this down. So, n1 sine theta 1 equals n2 sine theta 2. I don't like what the answer the book's given, because I do think it is worthwhile solving this properly to see what happens. Let's substitute 1 times sine of 0, oops, not sine of theta, sine of 0 equals n2 sine theta 2. Okay, so we don't have anything on this side, so what's the sine of 0? The sine of 0 is 0, so 1 times 0 is 0 equals n2 sine theta 2. Now, what we have here, we have two numbers. Sine theta is just a number. We have n2, that's a number. And when we multiply them together, the answer is 0. So, let's think about this. One of these two things has to be equal to 0. Now, n is a refractive index. It can't be less than 1. So that can't be equal to 0. So this has to be equal to 0. So let's write that in. Therefore, sine theta 2 equals 0. And if the sine of something equals 0, that means that something must be equal to 0. We could take the arc sine of 0, but we'd find that theta 2 equals arc sine of 0, which equals 0. So therefore, theta 2 equals 0. If it comes in at 0 degrees, it leaves at 0 degrees. But if I substitute 0 into here, can I figure out this number? Well, I could put 1 there, I could put 5, I could put 10, I could put 1,000,000. 0 times anything is 0. So I can't work out this number. Okay, so therefore, n2 is undefined. Theta 2 is defined, it's 0 degrees. And that's solvable, but this is not. Alright, I hope that clarifies that. I think the textbook gives a slightly less useful answer, just go straight to the undefined. Part of it is defined. Okay, let's have a look at question 6 now. So, question 6 says, a light ray travels from air to a substance, as shown in figure 18.4. Okay, looks pretty similar to 18.3. We've got hitting, we've got a perpendicular line with some angles, we've got air and a substance, but there is a slight complexity to this, so let's draw that up. So, this angle is between the incident ray and the surface, not the perpendicular. Remember, if we want the incident angle, we need this side of it. So we need to work out the complement. Now this is 90 degrees, the picture says so let's put that in. So if that's 90 degrees, that's 30. Complement means 60. Same thing here. If this is 90 as well, opposite angles, 45 complement will also be 45 degrees. Now we can do what we did before. n1 equals 1, theta 1 equals 60, theta 2 equals 45, n2 equals dunno, let's use Snell's law, n1 sine theta 1 equals n2 sine theta 2, so 1 times sine of 60 equals n2 sine of 45, So N2 equals sine 60 over sine 45 equals, well, we can do that in a calculator, sine 60 divided by sine 45, we get 1.22. Alright, question 7. Students conducting experiments to find the absolute refractive index of a piece of perspex obtain the results shown in the table below for the angles of incidence and refraction. Firstly, plot a graph of sine I against sine R. So a couple of things we're curious about there. Which comes on first is what's going to be the y-axis, what's going to be the x-axis. Okay. Secondly, we need a transformation here, because if we look at our table, we see that we have our values in degrees. It's not saying the sine of the angle of incidence, it's saying the angle of incidence I in degrees. So we need to change those first. So take the sine of 10, then the sine of 20, sine of 30, sine of 40, sine of 50, etc. Do it for the refraction index as well, because we want sine of R. So take the sine of 6, the sine of 13, sine of 19, 25, etc. and plot it on a graph. So I did that on Excel. I uploaded my numbers, I took the sines of everything. If you are doing this on Excel, the sine function needs radians, so just Google sine function and it will tell you how to put it in degrees as well, or to use a value that's in degrees. Now let's have a look at, what's the word I'm looking for, whether we put y on the sine y on the y, or the sine I on the x. So it's saying sine I against sine R. So the phrasing is always y against x, y versus x, y in relation to x. Okay, so whatever variable comes first, that goes in the y-axis. The table is kind of crappy in that regard, in that you should always have the x-axis as your first line in your table. But hey, can't do anything about it. So if you plot this, okay, so sine I on y, sine R on x. And I'll show you another way to derive that in a second, to figure out the best way in a second anyway. Let's draw that up. It will look something like that. Okay, it'll be a linear relationship. So from the shape of the graph, what is the relationship? Now, the answer for this is kind of weird. It gives you a calculation, but that's not a really for this. If you're looking at the shape, they're doing a calculation. The calculation doesn't mean look at the shape. And looking at the shape means look at the shape. Well, look at the shape of your graph. We can see based on the trend line that this is linear. We can certainly say what the gradient is, linear with m equals 1.52. If you do it in Excel, your number might have a little bit of variation. If you did it the other way, where you plotted plotted sine R on the y-axis and sine y on the what's the word I'm looking for? Sine I on the x-axis, then that might not, that'll give you a different gradient, but you could just as easily do it if you really wanted to. Alright, so and if you did do that, I'll just check the graph quickly. Not letting me move my x-axis. And well, look, you do it on Excel if you want to, but you get a number that will be lower than 1, and that's going to be a bit of a clue later on. Let's look at C. What is the refractive index? So, how can we figure out the refractive index from looking at this graph? Let's write out Snell's law for a second. We have N1 sine theta I equals N2 sine theta R. Now, N1 is just 1. It's air. Okay, it doesn't tell you explicitly in this that it's air, but it's saying students are doing experiments. It seems reasonable that they're going to have it in air. Okay, but they also they do say the words absolute refractive index, which means it has to be in relation to air. So n1 is 1. Let's ignore that. So now we're left with sine theta I equals n2 sine theta r. Now, if you've plotted this on an x-axis on a scale, then if this is on your y-axis and that's on your x-axis, then if this is a linear relationship, and we see it is, then this must be your gradient. Okay? If we rearrange this so that this was all alone, we'd get that sine theta r equals 1 over n2 sine theta I. So then that could be your x, that could be your y, and that would be your m. Okay, and remember here, m stands for gradient. So being as we've plotted this one, well, we can read that so that the gradient, okay, must be equal, and we can set the intercept to go through 0. That will give you a better number, because in this case we see that there is no plus or minus term here on the end. Okay, it's just straight up these two multiplications. So in this case, I've told the computer to take it through the y-intercept, through the xy intercept, and we have a look at that. M equals 1.52. Therefore, n2 equals 1.52, or if we rephrase that better, n of perspex equals 1.52. Now D, a bit tricky. Seems easy, but a little bit trickier. What is the angle of refraction if the angle of incidence is 54 degrees? Well, we don't have incidence angles here. We have sines. So we need to take the sine of 54, find that number in our graph, plot it, sine 54. Okay. We get that sine 54 equals 0.809, so let's go 81. I'm going to find that on my graph, so it's going to be just above 8. Go over to where it hits the graph, and we go down, we see that it's going to be around about 0.54. Okay. .54, and we know this is the answer is the sine of the refracted angle. So we need to arc sine this number to get theta r. So shift sine 0.54. We get that it is about 32.6. And let's check what our textbook says. Textbook in this case said, we're doing question 7, 32 degrees. Pretty close, okay? Obviously the better your graphing there is, the better your answer will be. Okay, let's head down to the next bit. Question 8. Alright, now this one is about relative refraction. If you're watching this video in 2017, we're not doing relative refraction. Unless you're in class I've talked about this idea, really don't worry about this too much. It's not a hard idea, but I'm just going to show you. Now, the font on my digital version of this is giving me that if I zoom in enough, I can now see it's a proper equal sign. So it's asked us to use two definitions for N of water, and I'm going to use an arrow here, just helps me think about this, to glass. We're using W in this case stands for water, and this one stands for crown glass. And it wants us to use two definitions. Either this equals velocity in water over velocity in glass, or N of glass over N of water. Now, where can we find this information? There was a table back at the start, so let's go back to that table. Okay, so that very first table we saw, let's list these down. So V in water equals 2.26 times 10 to the 8. Velocity in crown glass, so there are 3 types of glass there, make sure you choose the right one. 1.97 times 10 to the 8. We need our N in water, so that's going to be 1.33. And we need our N in glass, that will be 1.52. Okay, so let's use these definitions here that they've provided for us to compare and see, do we get the same value from both of those? That's what it's asking about here. So, VW over VG, VW 2.26, 10 to the 8 over 1.97 times 10 to the 8. Like before, 10 to the 8's cancel. Okay, equals 2.26, 1.97, 1.97 gives us 1.147. They do round it off at 1.14, but let's go a little bit more precise. Let's use our other definition, Ng over Nw. Ng over Nw equals 1.52, 1.33, gives me 1.1428. So if we cut it off there, then yeah, it's identical. If we keep going a bit further, there it's not, and that because, well, they've only given us 3 decimals here, so I can't really use these numbers here anyway. If we look at this, I've got 3 decimals. Yes, that would round it up to 1.15, but I suggest that they've just cut off that last one rather than actually rounded it. So get 1.14, and that is what the textbook says we should expect to get, an answer of 1.14. 9. Okay, now we'll do this one last in this video. There's quite a lot of questions in text for this one, and they're quite big. So this will be the last question, and 10 to 19 will be in another video. Alright, we've got a drop of soapy water. It's placed onto a block of glass, as shown in the figure to the side. A ray from a laser was shone into the water at an angle of 38 degrees. Calculate A, angle of refraction in soapy water. B, angle of refraction in the glass. C, angle at which the ray exited the glass on the other side. And D, the relative refractive index of light going from soapy water to glass. So A to C is the important bit. Don't worry about D. I'll show you how to do D, but A to C is the important stuff to know from this question. So let's draw this picture, and I'm going to draw it pretty big because we're going to have a few angles in it. Here's our glass. Here is our soap bubble. That'll be 90 degrees. Oops. Let's try to get that actually go to that point. Here is our laser at 38 degrees. And so there's our normal on the other side. If this is air, that means it's n equals 1, n equals 1.38, and n equals 1.5. So that's all the information given to us inside this question. Now, here, 1 to 1.38 means it's going to bend towards the normal, so we're going to get a small angle on that side, and then when it hits over here, this angle, theta R1, will equal the next theta I. Alright, and then if we keep going through here, again, it's small to a bigger number, so it's going to bend even more. Get to the other side, and then this angle will equal this angle. Okay. And then finally on the other side, it will go from a heavy medium back into air, a light medium, and so it will probably bend off some more, and we will have to work out that angle. Okay, so let's do it step by step. So A, we want the angular refraction in the soapy water, so just this first one. Let's list it out. It's just Snell's law. The fact that we've got 3 things to look at doesn't matter. We just consider one at a time. Sometimes these things want you to do relative refractive indices, but Snell's law is better to be really, really good at because it will just deal with all the situations. You don't need to worry about a relative refractive index. You can calculate it pretty easily, and I'll show you where it pops up in this equation as we're working through it, but do not really worry about it. So, N1 equals 1, it's air. Theta 1, our incident angle, 38 degrees. Theta 2, we don't know. N2, the medium we end up in, 1.38. Snell's law, let's substitute. n1 sine theta 1 equals n2 sine theta 2. Now let's just go back up here for a second. Okay. We saw that the n of water into glass is just the n of glass divided by water. Okay. So if we wanted the relative index between this, we would take this n1 and divide it over there, and then we would be able to apply to that. Okay. But I don't really care to worry about that too much. So let's keep going. n1 is 1 sine theta 1 sine 38 equals 1.38 sine theta 2. Okay, let's rearrange. The 1 goes away. Sine 38 over 1.38 equals, and let's take the arc sine, equals theta 2 equals, well, do that on calculator. Sine 38 divided by 1.38, and we want the arc sine of all of that, 26.5 degrees. Textbook gives us 26.5 degrees. Great. First step down. Let's do our next one. So now we're going from, so if this is 26.5 degrees here, this incident angle going from the water into the perspex, or glass, whatever it is, yeah, glass, will also be that same angle. Okay, so this refracted ray becomes the next incident ray. So B theta I equals 26.5. N1, sorry, theta 1. N1, well, it's not air anymore, it's soapy water, 1.38. N2, glass, 1.5. Theta 2 equals, we don't know. Okay, that's what we're going to have to figure out. Okay, so let's do the same thing. N1 sine 1 equals N2 sine 2. 1.38 sine of 26.5 equals N2 1.5 sine of whatever our other angle is. Let's rearrange it. So that divided by 1.5, and then we want to take the arc sine, so let's do it step by step. 1.38 over 1.5 sine of 26.5 equals sine of theta 2. Let's solve this. So sine of 26.5 times 1.38 divided by 1.5. Buttons on this calculator, it's stiff. 26.5 times 1.38 divided by 1.5. Alright, so we have here that sine theta 2 equals 0.41. Take the arc sine, we get that theta 2 equals 24.2 degrees. And double check your textbook, we see it's the right answer. Last step from, so again, this angle, which we just figured out is here, sorry, a bit hard to see that then, is here, is going to become the new incident angle. They are parallel lines connected, transverse line, Z rule, that's going to be the same as that. So this now becomes our new incident angle, 24.2. N1 equals 1.5, it's starting in the glass. N2 equals 1, it's going into the air. Theta 2 equals dunno. Now, let's make a prediction. Think about this. These two surfaces are parallel, and the top of this bubble is essentially flat, so it is also effectively parallel to this and to this. So remember, parallel surfaces should have the same incident and refracted ray after it goes through. It's gone through two things. Will it affect it? Okay. It's a good thing to sort of say, okay, I think this might be an example there. And let's see if we're right. So, well, I know I'm right, but let's see if the math tells us we're right. So, N1 sine theta 1 equals N2 sine theta 2. So, 1.5 sine of 24.2 equals 1 sine of 2, so that 1 we can ignore. So we're going to have the arc sine of 1.5 sine 24.2 equals, don't know what that was meant to be, theta 2. So sine of 24.2 times 1.5, take the arc sine, we get 37.9 degrees, which is rounded at 38 degrees. So being as we had some rounding errors obviously going through that, the fact that we've almost arrived back at the same number is pretty good. Okay, last bit, relative refractive index of light going from soapy water to glass. Okay. So N of soapy water into glass. Okay. Let's go back, let's double check what we had before. So if we have something into something, the final bit ends up on top, the starting bit ends below. So that's going to be N of glass over N of soapy. 1.5 over 1.38, 5 divided by 1.38 gives us 1.09. Okay, so that's the end of those first 9 questions. Questions 10 to 19 will be done in later videos. Thanks, guys.